All right, we all know quantum mechanics is weird. But what if I told you we're about to look at an idea that takes that weirdness and cranks it up to 11? We're going to explore how two pretty radical theories might actually fit together to completely rewrite our picture of reality. The basic idea? That the subatomic world is way more alive, way more interactive than we ever thought. Let's dive in.
You know, the standard quantum story is kind of like a one-way street. You've got this wave of probability, the famous wave function, and it's basically the boss. It tells a particle where it's allowed to be. The particle just listens. But what if that whole picture is missing something huge? What if it's not a monologue, but a conversation? What if the particle can actually talk back to the very wave that's guiding it? This idea is called back reaction, and honestly, it could change everything. So let's really get into this whole problem of back action. For the better part of a century, mainstream physics basically just assumed it wasn't a thing. The wave commands, the particle obeys. End of story. But a handful of physicists looked at that and said, hang on a second, what if that's too simple? They started proposing that reality is a constant dialogue, a feedback loop that's happening at the most fundamental level of existence.
And that gets to a really deep assumption in all of physics. See, standard theories love to treat things as closed and linear. It's like putting the universe in a neat, tidy box where everything is predictable. But what if that's just an approximation? A convenient story we tell ourselves? What if reality is actually messy, open, nonlinear, and it's constantly organizing itself? Especially when things get pushed far away from their nice, stable equilibrium state. Okay, so to build this new, dynamic picture of the universe, we're going to need two key ingredients. Think of it like a computer. First up, we need the hardware, the actual physical stuff reality is made of. And for that, we turn to physicist Shan Gao, who came up with an absolutely wild idea about how particles, well, how they move. So whatever you learned in science class about a particle moving smoothly from point A to point B, just throw it out the window for a second. Gauss' theory is called random discontinuous motion, or RDMP. And it says a particle is constantly making instantaneous random jumps. It literally disappears from one spot and reappears in another, without traveling through the space in between. In this picture, the wave function isn't pushing a little ball along a path, it's just telling you the odds of where that particle is going to pop into existence next. Wild, right? So if you could zoom in on a tiny fraction of a second, you wouldn't see a clean line. You'd see this cloud of appearances, a frantic storm of the particle just showing up all over the place. And it's this constant, chaotic jumping that gives the particle its effective presence in the world. It's not in all those places at once, but it's jumping between them so fast that it might as well be. Now, why is this so important? What's the big deal? Well, it fixes a really old, really annoying problem in physics. The old model of an electron being a continuous charge cloud meant that the cloud should be repelling itself, which is something we just don't see in experiments. But in Gauss' model, that cloud is just an illusion. It's an effect created by one single particle jumping around like crazy. And since that particle is only ever in one spot at any single instant, it can't repel itself. Problem solved. It's so elegant.
Okay, so if Gauss jumping particles are the hardware, we still need the operating system, right? The software that tells the hardware what to do. That brings us to the second piece of our puzzle, Jacques Sarfatti's post-quantum mechanics. This is the framework, the new set of rules for this interactive reality. Sarfatti's post-quantum mechanics, or PQM, basically takes the old rulebook and sets it on fire. It says reality is a nonlinear, open system. There's a pilot wave guiding the particles, sure, but, and this is the whole game, the particles' actions feed back and change the wave itself. They're stuck together in this intricate, self-organizing dance. This is the two-way conversation we've been looking for.
Let's break that down a bit. PQM starts by saying reality is not a sealed box. It's designed to describe what happens when things get pushed really far away from that stable, predictable quantum equilibrium. But here's the catch. To stay in that weird, exotic state, you need some kind of physical mechanism that allows for this back reaction. You need something that's constantly pumping the system with energy, keeping it all stirred up. The theory itself demands a physical engine. So where on earth do we find one? And this, right here, is the light bulb moment. This is where it all clicks into place. On one hand, we've got Sarfatti's theory, which is screaming for a physical engine to make back reaction happen. And on the other, we have Gauss' theory, which describes this totally bizarre way that particles actually move. You can probably see where this is going. They fit together like a lock and key. It's actually stunningly simple when you put it together. Gauss' randomly jumping particles are the physical engine that Sarfatti's post-quantum framework desperately needs to work. The hardware we talked about was built to run this exact operating system. They were made for each other. So here's how the process works, in 4 simple steps. Step 1, jump. A particle does its thing and takes one of Gauss' random leaps. Step 2, kick. Every single one of those jumps gives a tiny, non-linear kick back to its own guiding wave. It's talking back. Step 3, pump. The combined effect of all these constant kicks is like continuously pushing a kid on a swing. Physicists call it frolic pumping. And finally, step 4, violate. This constant pumping shoves the system far away from its comfortable equilibrium state, creating a space where the normal rules of quantum mechanics can actually be bent or even broken. I mean, just look at how perfectly these two ideas mesh. On the left, you've got Gauss' theory, which gives us the physical cause, the actual nitty-gritty motion of the particle. And on the right, you have Sarfatti's theory, which describes the effect, a whole new kind of physics driven by back reaction. The random jumps from Gauss' model literally are the physical kicks that Sarfatti's model needs. It's a complete, beautiful picture of cause and effect at the deepest level of reality. So, what does this all mean for physics? What's the big picture here? Well, this unified theory isn't about tearing down everything that came before it. It's more like adding a new, higher floor to the building. It creates a more complete hierarchy of how reality works. Think of it like a ladder. On the bottom rung, layer 0, you've got your standard textbook quantum mechanics. No back action, simple as that. Climb up a step to layer 1, and you've got theories like Bohmian mechanics, where you have real particles, but it's still a one-way street. Layer 2 is where things get interesting. You start to see hints of back action, but only in nice, stable systems. But then, at the very top, layer 3, that's our new synthesis. That's PQM plus RMDP. That's powerful, universe-shaping back action in systems that are wild and far from equilibrium. Each layer gets us closer to the whole truth. And this quote just nails the whole idea. Equilibrium without non-equilibrium is sterile. Basically, if you only study the calm, stable stuff, you're missing half the picture. But non-equilibrium without rigorous equilibrium is hand-waving. You can't just make up crazy ideas about chaotic systems without grounding them in the basics. You need both, the calm and the chaos, the stable and the exotic, to have a complete theory of reality. Which, of course, leaves us with one final, absolutely mind-bending question. If particles can really kick back, if they can actively shape the wave that guides them, what does that make possible? The people who work on this stuff think it could be the key to things straight out of science fiction. We're talking about the potential for faster-than-light communication, or maybe even understanding the physical machinery of consciousness itself. It is a radical, incredible vision of a universe that isn't just passively unfolding, but is actively co-creating itself one quantum jump at a time.